Hi, everybody. This is Mr. Folly, and welcome to 9.2. Yeah. So, in this one, we have an oldie but a goodie coming back to see us, which is potential energy diagrams. So, potential energy diagrams compare what happens with our reactants to our products and the path that it takes. So, if you notice, your reactants are going to start going uphill. The reactants will always go uphill. Okay. Now, potential energy diagrams have two forms. They could be like this one where they end a little lower, or like this one where they end a little higher. Okay. So let's look at each part bit by bit by bit by bit by bit. Let's see if I can zoom out a little bit. Oh, no. If you give me some more magic toolbars here, standard, that'll do it. Oh, almost. So let's zoom out of this guy a little bit. Okay. So reactants are your starting substances. Products are your ending substances, right? Your transition state is this right here. The transition state is also known as the activated complex, is the temporary arrangement of atoms as a transition state between reactants and products. It is represented at the top of the potential energy hill in a PE diagram. It is a point. The activated complex is at the top of the hump, same as a transition state. And this one, the one's a little bit different. This is letter B, okay? The activation energy is the energy to get from the reactants to the highest hump. So notice how if this had a number of, say, 800, the activation energy would be from 600 up to 800. The activation energy is the minimum energy reactant molecules must possess in order to have successful collisions from the activated complex and then eventually the products. Delta H is the energy from the reactants to the products. That would be letter D. Okay. Negative if it ends down. This would be exothermic, right? Delta H is negative. And this one right here, delta H, would be positive. Okay. And that's pretty much the big part of it. Let's go back up to our 115 and let's do some sample problems with it, okay? Endothermic, energy change where the products have more energy than reactants. It ends higher. That means it looks like this. It absorbs heat. Products will be colder. Exothermic, energy change. This is endo. Energy change where the reactants have more energy than the products. The reactants will have more energy than the products. Still has a hump going up, right? Ends lower, releases heat. Products will be hotter. Catalyst speeds up a reaction in both directions. It lowers the hump. So what that would look like, let me go with a purple catalyst. It would have a lower hump. It's almost always shown as a dashed line. Okay? And it speeds reaction in both directions. Like a tunnel through a mountain. So in a tunnel through the mountain, if here's my mountain, and Mr. Folly drives, Mr. Folly and me used to have to drive over, here's my car, over Mount Hoosier to get to LT every day. But then, thanks to the great taxpayers of Illinois, there's now a tunnel that I can take that would make it quicker for me to go to work. Well, guess what? I can take that same tunnel going home, so it makes it faster both ways. Okay? Catalyst speeds up the reaction in both directions. It lowers the hump. It's shown as a dashed line, like a tunnel through a mountain. It actually changes the mechanism. It doesn't just lower the energy of the old mechanism. A catalyst affects the slowest step of a reaction. The catalyst changes the mechanism. Think walking versus an airplane. So if I want to go to New York and I was walking, or I wanted to go to New York and I'm on an airplane, it doesn't even make sense to compare those rates, right? It's totally different. Okay. The other thing I want to do with this right now is humps equals steps. This has two steps. How do I know it has two steps? It has two humps. Does that make sense? The first step, energy goes up, is endothermic. The second step is exothermic, but overall, it's exothermic. Remember, exo means you lose heat. Okay? Now, if I said draw a reaction with 4 humps. Uh-oh, I only got 3 in there. Not 4 humps, 4 steps. Remember, each step is represented by a hump. Okay? The reverse reactions start on the right and go left. Endo and exo flip. Delta H flips. Remember, when bonds are breaking, it absorbs energy. This would be bonds breaking. And when bonds are forming, it releases energy. So going down, that would be forming. Whoa. You should be able to label that on it too. Okay. So let's take a look at this guy. Bonds breaking. Let's zoom a little bit more. Just a little bit more. So here we go. We're going to look at this. This is a weird one because they're usually rounded instead of flat, but we'll deal with that. Reaction pathway. Let's get some numbers. The reactants. What's the number for the reactants? I'll switch to my little highlighter friend here. Reactants. Boom. 40. Products. Products are here, and that number is 125. All of these are going to be in kilojoules. Okay. EA. EA is from the reactant up to the transition state. So it's from 40 up to 335. So EA is going to be 335 minus 40, which is going to be 290, 285. Uh-oh, I'm a little worried about my math today. Yeah, it's 295. I swear I can do math. 295. Okay. The transition state is just the number that's placed up on top. Okay. So my transition state, I'm running out of light colored things to use. My transition state is up here on top. And my value for my transition state would be 335. Delta H is products minus reactants. My products are 125. My reactants are 40. 125 minus 40 is 85 kilojoules for delta H. Okay, reverse reaction. So that means I'm going the other way. So my reactants are now my products. Whoa, dude, that's just like crazy. So if it's the reverse, I'm just going to flip it. I'm going to call this reactants with like a big letter of shame here. So reactants are on the right. The reactants are 125. Products are now 40. My EA is from my reactants up to the top. So this is 335 minus 125, which is 210. Remember, all of these are kilojoules. Okay. The transition state, that's going to be the same. That's going to be 335 kilojoules. I'll throw some kilojoules on here because who doesn't love a good unit? Okay. Kilojoules. I did the transition state. Delta H, remember, is products minus reactants. Remember how to rename them? So 40 minus 125 is negative 85. So notice the magnitude is the same, 85, but the sign is different. That's it. That's all you got to do. That's not too bad, I think. I think you'll do great at it. And to that, I'll say, toodles.